So now that you can draw a basic exponential or log graph, we need to also be able to make our transformations with them. Now we've made transformations with exponential graphs before, although that was a while ago, so we need to refresh our memory. We haven't actually made transformations with log graphs before because those are new and we've just learnt them this week. So here are our basic rules for how we move a graph left and right or up and down, that's just sliding it around, or how we reflect it left to right, or how we reflect it upside down. Now, there's basic rules. To move it left to right, just replace the x with x plus or minus something. So if you know what a basic exponential graph looks like, look at what the x is doing. It's sitting in the index. If you put a +1 up here, it shifts your basic exponential graph 1 unit to the left. Remember, it's the opposite way that you might think. And if you had a -1 there, it would move your graph 1 unit to the right. Now, that's quite different from how you move it up or down. To move it up and down, the technical definition is that you replace y with y plus or minus something. And that works when you've got a circle or a relation or something like that that's actually not a function. When we have functions, we normally write them as y equals some stuff. So we don't really want to write y plus something equals some bits. We just want to write y equals. So instead of replacing the y with something, we tend to rearrange those and say, let's take 1 off both sides in this case. We don't want y plus 1. Let's have just y. And when we do that, we're basically taking 1 away from both sides, aren't we? So we end up writing it, whatever we would have had here, let's say we had y plus 1 equals 2 to the power of x. When you do it this way, it's the same with these ones. It's the opposite way that you might think. So adding 1 to y actually moves the graph down, which doesn't quite look logical, does it? But when we rearrange it and write it like this, and here this is the same graph, I've just subtracted 1 from both sides, now it does look like a logical way to move the graph down. The easy method that I like to remember for functions, just tack the number onto the end. And it is the way that makes sense. So if we have a graph that we already know and we want to move it down 1 unit, it looks like that, which is quite different from having the -1 up here. That's moving it left and right because it's tied in closely with what the x is doing. Similarly, if we have our basic log graph and we want to move it left or right, we would change the x to x plus or minus something. So for example, this is our basic log curve, but it's been moved to 1 unit to the left, the opposite way that you might think. And yet if I have the basic log graph and then I just chuck a great big +1 on the end, that's now moved it up. Because what I've done is I've tacked the 1 onto the end. It's not tied in closely with what the x is doing. And what is the x is doing? Well, it's having the log taken of it. Alright, so that's moving things up and down, left and right. Check if it's tacked onto the end or tied in closely with the x. To reflect things left and right, we just replace x with -x. So that means we could have this graph looking like this. Or our log graph looking like that. And to reflect upside down, we replace the y with -y. Now, it's not often written this way. Look what happens if I replace the y with -y. Sure, I've reflected it upside down, and this is that graph upside down. But we don't normally write it like this, do we? We write y equals something, and that means that if we multiply both sides by -1 here, we're going to end up with the negative hanging out the front of the 2 there. Okay, so it's hanging out the front of the 2, it's really related to the y, and we flipped it vertically. Whereas if our negative is up in the index like this, then it's tied in closely with what the x is doing. We've changed x to -x, and we've reflected left to right. Our log graph also can be reflected upside down just by changing y to -y. But of course we wouldn't write it like that. We would write it like this, and the negative would be out the front. And I've simply multiplied both sides by -1 there to transfer the look of it. Alright, so we've got some examples here. This is not an exhaustive list. Of course we can move both curves, up, down, left, right, reflect them. But let's just look at these 4 examples to get some practice. Now, What I do first is think about what my basic curve looks like. So I'm going to do a little mini sketch of it over here. So y equals 2 to the power of x minus 1 is going to be a lot like y equals 2 to the x. And I know what that looks like. I've got a basic sketch. It goes through 1 there. Now this graph, I've moved it. How have I moved it? Left, right, up, down. What's happened? It's gone 1 unit to the left. The opposite way than you would, sorry, I've got it wrong. It's gone 1 unit to the right. Okay. Now think of what your normal graph looks like. Okay. We're going to move that to the right. So we have one known point straight away. Is the asymptote going to move? No, it's shifting along, so it's basically staying there. So draw the asymptote first. That gives you a good base to know what's happening. Now you've got your basic shape, still going to be roughed in much the same. Label your graph. And now we need to note anything of importance. We need the intercept and we need another key point. Now I already know that normal intercept is at 0, 1. So if I've moved that point 1 unit to the right, it's going to be over here at 1, 1, isn't it? So I have a known point already, 1, 1. May as well label that. That was really easy to find because I just took a point that I knew and I moved it across one. That leaves me not knowing this point, and I'm going to have to do some work to find that now. Now, how do I find a y-intercept? I need to let x equal 0. So there's a little bit of working to do. When I do that, sub 0 in, I'm going to have 2 to the power of 0 minus 1, that's minus 1. And 2 to the power of minus 1, that's the same thing as 1 over 2 to the power of 1. It's just a half, isn't it? So I can label this point here now as a half. That's all I need. I've got my intercept, I've got my asymptote, I've got one other point, and I've labelled the curve. So that one's done. All right, on to the next one. I have a basic exponential curve. It's like y equals 2 to the power of x, but what's happened to it? Well, it's got a negative sitting out the front here. Something's been replaced with a negative. Now, if I rewrote that by multiplying both sides by -1, I can see that this is what's happened. My y has turned into a negative y. So if I've changed the y's and negative y's, that means I've changed it vertically. I've flipped it upside down. So think about what your normal curve looks like and imagine what it's going to look like when you turn it upside down and now do a decent sketch of it. The asymptote is still in the same place. It's almost like the fold line where we flipped it. But now it's looking like this. It's upside down, and instead of being 1, this is -1. And instead of my usual known point of 1, 2, it's going to be 1 minus 2. So rather than actually figuring out that point by subbing things in, I can just take things that I knew off this graph and put them onto my new one. And that's everything that I need to show. All right, the next one. I'm graphing log curves now. So my basic log curve, I need to think through what that looks like. It looks like this, doesn't it? And it goes through 1 here and has an asymptote like that. All right, this first one, what's happened to it? Well, it's got a big +2 tacked onto the end. Are there brackets here? No. If there were brackets, I'd say that we've moved it sideways and the x has become x plus 2. We've moved it 2 units to the left. But there's no brackets. That means that we're only taking the log of the x. The +2 is tacked onto the end like an afterthought. And in fact, this is the same thing as if I subtracted 2 from both sides and it looked like that. Obviously, I don't need to write it like that, but it's the same. So what I've actually done here is I've moved my normal graph up 2 units. All right, so let's go to draw it. The asymptote, is that going to have moved? No, it's gone up, so it's still going to be in the exact same spot. All right, this known point that we have at 1, has it moved? Yes, it's gone up 2. It's now going to be sitting at 1, 2. So that's a point that I know on the curve. I may as well graph that now, and that's nice and easy to find. All right, now what's the basic shape? It needs to have a shape like this. So you can now just rough it in. Basic shape coming up like that. All right, what are we missing? We need to label it. We've got a point. We've got the asymptote. What are we missing? The intercept. All right, so we've got a bit of work to do. How do we find an x-intercept? We need to, that's it, let y equal 0. All right, let's let y equal 0 and rewrite this now. That means we've got 0 is equal to the log of x with a base 2 plus 2. All right, how do I get the x by itself? Get rid of this plus 2 by subtracting 2 from both sides. So I've got minus 2 is equal to all of this. How do I figure out x now? Well, I can retell the story here to rewrite it as an exponential expression, can't I? And just as normally when I'm using my logs, I can retell a story around this way, if everything's on the other side, it still works. I can say 2 to the power of minus 2 equals x. 2 to the power of minus 2 equals x. All right, what is 2 to the power of minus 2? Well, that's 1 over 2 squared, isn't it? Which is 1 over 4, or a quarter. So now I can go ahead and label that as 1/4. And I've got everything on my graph that I need. Now, there was a little bit of work to do to find that intercept. Sometimes there will be. But just remember how to find an x-intercept, let y equal 0, how to find a y-intercept, let x equal 0, and then solve that little equation. All right, for the last one, what's happened to our basic log curve this time? It looks like we have changed the x into a minus x. Now, this looks like a red flag. Didn't I tell you earlier that we can't take the log of a negative number? I did. Well, how are we going to take the log of minus x then? Well, x is going to have to be negative. If x is negative, we're going to have a negative number. And a negative times a negative makes a positive. So it is going to work. Now, the way to think this through is this is our normal log curve, like this. If we've replaced x with negative x, we've basically just flipped it left to right. So we've flipped it like that around the y-axis. So it's going to look something like this. And instead of going through 1, it'll go through -1. And instead of having a nice simple point that we can plot like 2, 1, it's now going to be -2, 1. Now, it doesn't matter if the point that you plot is not to scale. You just plot a point and label it with a point that does exist. And if you like, you can check that that point is correct. Let's sub in -2 for x. -2, well, that's just 2. So if we have the log of 2 with a base of 2, what does that equal? Well, 2 to the power of 1 is 2. So sure enough, y would have to be 1, and it works. But taking a point that I've learned on my normal curve and flipping it over, I just find that quite an easy way to do it. Now, obviously, my graph is not all that well to scale here. Perhaps I should have drawn it a little bit more like that so that when I label my point, it looks a little bit better. But mathematically, there's nothing wrong with having the scale on each axis different. So don't worry. You just need the basic shape, you need the asymptote, and then you need to label your graph.